You are welcome to the U21's episode U2 Past Question Review class. In this episode, we are going to be considering past questions from Ordinary Differential Equation, ODE. If this is the first time of visiting the U21's YouTube channel, please subscribe, like, and share our videos. You can also make a comment, either in appraising our work or perhaps in areas that you feel we can improve more. We will welcome such comment. If you're here to subscribe and you've been visiting the GMAT41's YouTube channel, what is holding you back? Remember, from here, there are interesting facts you can always learn. Remember to inform and invite your friends also so that they can visit our YouTube channel. Encourage them to also subscribe as we carry you along, teaching you important concepts in your studies. Here on the board, we have our very first question, and I would like to read. Solve the equation 2, open brackets, 2x raised to the power 2 minus y raised to the power 2, close your brackets, dx, minus xy dy equal to 0. So we are required to solve this differential equation. From our full range of learning classes, I have always maintained for ordinary differential equation, if you are given any problem to solve, the very first thing you are required to do is to be able to identify the form of ordinary differential equation you are dealing with, especially if it is a first order ordinary differential equation, FODE. Looking at the board here, this question is actually a first order ordinary differential equation. How did I get to know that? Look at this differential coefficient, it's simply dy. There is nothing like d2y there. Look at this one, it's simply dx. Nothing like the squared x. Are you following, right? So the variables here have been differentiated only once, telling us that this is a first order ordinary differential equation. Now that we've identified that it is first order, we need to know the type or the form of first order differential equation it is, because we have different forms that have different ways of solving them. A critical look at this equation, you will agree with me that this is a homogeneous first order ordinary differential equation of degree 2. The problem is as good as solved because we've been able to identify the type of FODE that this question is. The next thing we've got to do is applying the method that is relevant to solving homogeneous first order ordinary differential equation. Please, at this point, I would like to take this moment to ask you to go through our channel, and you would see a video release where I presented the onmakers FDU, FNU homogeneous FODE theorem. And so this very first question is significant because I've decided to solve this particular question as question number 1 in episode U2 in order to help you learn how you apply the onmakers FDU, FNU theorem. I should do that swiftly. The question given to us here is 2 brackets 2 x raised to the power 2 minus y squared dx. Now I'm going to transfer this minus xy dy to the right hand side, so it's simply going to be xy dy. And then I'm going to recall the transformation we use in dealing with homogeneous FODE problem. And the transformation is y equal to what? Ux. According to the onmakers FDU, FNU homogeneous FODE theorem, I stated that as long as we can consciously eliminate x from this differential equation, there is a particular formula that we can use in breaking this homogeneous equation down to a separable variable equation. And so I'm going to do that. Is that okay? At this point, I'm going to simply eliminate all the x from the given differential equation. You see, I did this consciously. I just decided, let's go. Cancel it off. All x from this differential equation. And now what I'm going to do, because I've cancelled all x from here, that leaves this transformation with simply y equal to u. That is just the idea. Which means that going back to this homogeneous differential equation, wherever I see y, I will substitute u. Are we together? Good. And so we are going to get, it implies that 2 bracket, look at this is also 2. And so I'll write 2 minus this y will automatically change to u, and I will square it. Is that okay? Then proceed, this one will become u. This y will change to u. Are you following, right? And then I am going to multiply this by dy. This is interesting. At this point, I am going to apply the Ohmmaker's homogeneous fluid theorem. But first, let us identify our fd and fn of u. This term that is getting the differential coefficient dx is simply our fn of u. And then we've got this is our fd of u. That represents denominator. The d there. Anyway, it's not significant to what we are dealing with here. But that's just what I choose to call them. Let's move on. I shall now apply the formula, recall, from the Ohmmaker's homogeneous fluid formula. So this is the formula we are going to use to reduce this equation directly to separable variable, making the problem 1 plus 1 for us. We shall substitute into this Ohmmaker's homogeneous fluid theorem equation there. And so let us speak. F du is simply this u here, and then it's going to be u divided by Fnu is this term 2 bracket 2 minus u raised to the power 2. So I'm going to write 2 bracket 2 minus u raised to the power 2, then minus u times what we call the f of d of u. And f of du, like we have identified, is simply what? U here. So I'm going to multiply by this u times u. Then this will be multiplied by our differential coefficient u. Remember that I've transformed this to a variable u, no longer y. And that is why I've got my u here, du. And that is going to be equal to 1 all over x dx. The right hand side is very simple, okay? That part always gives us ln x once we integrate. And so we don't have much problem there. Now simplifying this term, we are going to get u all over. Watch and see, these two, we open up this bracket, we've got 4 minus 2u squared. Then this will give us minus u squared. Now look at the like terms. Minus 2u squared minus u squared will give us minus 3u squared. So the denominator is simply 4 minus 3u squared, then du equal to 1 over x dx. This is the proper separable variable equation form of the homogeneous equation given to us here. Let me indicate this is our SVE. Is that okay? We've gotten the separable variable equation form of this given homogeneous equation. And this is in terms of u and what? X. At this point, we simply integrate. I shall introduce my integral sign here and introduce my integral sign here. But like I said, the right hand side is not a problem. As a matter of fact, in this theorem, simply integrating this, I could say that all this term, all this u term on the left hand side is equal to ln x. It's equal to what? Ln x. Because integral of 1 over x dx will always give us ln x. And so I can simply just work out that right hand side without stress. And then I would know that I'm left with the left hand side. Okay, we are moving on. I want to integrate this term. Integral u all over 4 minus 3u raised to the power 2 will give us what? Of course, u substitution is going to solve that for us. Are you having challenges with basic integration? If you are, please feel free to contact GMAX41. Alright? You can use the number shown on the screen, either to call or WhatsApp us, and of course, we're going to assist you. Is that okay? Now, we are moving on. Looking at this, if you differentiate this denominator, we are going to get minus 6u. Minus 6u. And for that reason, because the numerator is simply u, I will multiply the top and bottom by that constant coefficient, minus 6, which I obtained by differentiating this denominator. Now, if the denominator gave me minus 6u, and you have that u in the numerator, the difference is just that minus 6. And therefore, the integral of this term is negative, you do 1 all over that 6. This negative is coming from that minus 6. Is that okay? Which you got as a coefficient of u by differentiating the denominator. So simply do negative 1 over that 6. and then ln of the denominator 4 minus 3u squared. Good. We've done the integration of that part. So equal to the right hand side is ln x, then plus. Because the term we have here after integrating this bears ln. And the one we have on the right hand side also bears ln. You know, ln is logarithm to this e. So it shares the same properties as logarithm. For that reason, the constant of integration will be ln c. We are done integrating. We've solved the problem. This is per se the answer. But of course, in objective case, you might not see this option there just like this. The option is not there. Are you following, right? So you are required to simplify this further. And of course, in mathematics, you know that simplification is very important. You've got to continue simplifying until you get the simplest form. And we can do that here. For example, this is bearing negative 1 over 6 ln this equal to this. Are you following, right? I can decide to clear the fraction. But while clearing the fraction, what stops me of applying in this the law of logarithm here, law of logarithm, whereby I'm adding these two terms, pick one of the lns, and then multiply the terms you have there. I'll do that simultaneously, please. Clearing the fraction, I'll have negative ln 4 minus 3u raised to the power 2 equal to, coming here, I'm going to get ln x raised to the power 6 times c. Now I'll enclose this in brackets. What have I done? I've simply applied addition law of logarithm to the right hand side. Is that okay? And then cleared the fraction. If I'm using 6 to multiply this term, the 6 multiplying this part will divide itself and it goes off. You'll be left with minus 1, which will multiply this ln to still give you that. Use the 6 to multiply this term. Applying power law of logarithm, 6 times ln x is the same as ln x raised to the power 6, which is why you have this x raised to the power 6 there. Use the 6 also to multiply this. Now, power law of logarithm moves the 6 to become power of that constant of integration c. C raised to the power 6 will still give you a constant, and that is why I simply left it as what? C. Correct. Now, I would like to substitute the value of u into this equation. Come back to this place. Remember, we use the transformation y equal to what? Ux. It simply means that u will be equal to what? Y over x. Because your final answer in this question is meant to be in terms of x and y. The question was given in terms of x and y, not x and u. Therefore, once you are done solving this, you're expected to put in the value of that u. If y is equal to ux, then u will be equal to what? Y over x. Let's substitute that and see. Please, I am going to solve this or work it out once. If I'm substituting the value of u here, which is y over x, you notice that we will do some form of simplification. That's subtraction of fraction there. Are you getting me right? So that gives us negative ln, open bracket. This is y squared over x squared. So use that x squared, work out the LCM. You are going to get 4x squared minus 3y squared all over x squared. Correct. And that is going to be equal to ln cx raised to the power 6. Now, I want to look at something in this option here to guide me in knowing what next to do from here. Now, if you look at the options given to us, point number 1, there is nothing like logarithm to this e, that is ln, nothing like that. Which means I have to find a way to eliminate this ln. Is that okay? That's point number 1. Secondly, I noticed that there is, I noticed that there is nothing like negative power here. Nothing like what? Negative power. Therefore, I cannot multiply both sides by this negative, because if I multiply both sides by this negative, then if the negative comes here, applying power law of logarithm once again, the negative will go as power of this x raised to the power 6, which automatically makes this x to become x raised to the power minus 6. But there's nothing like x raised to a negative power there, which means I am not allowed to move this negative from here to the other side. Hence, what will I do to make sure that this negative clears off? Because, like I said, there is no negative power of x here. The only way I can do that is to apply a law of logarithm, which tells us that if you have a fraction in front of a logarithm term, are you following, right? If you turn that fraction upside down, that is kind of inversing it. The sign behind that logarithm will also change. So if I want this to become positive, Then this x raised to the power 2 will go up. 4x squared minus 3y squared will come down. I hope that is clear. And doing that, I'm going to get ln x squared all over 4x squared minus 3y squared. And then this will be in bracket equal to ln cx raised to the power 6. And because both sides have the same coefficient of this ln, that is logarithm to base e, you can do what? Cancel the lns off. Alright, just simply talking about take exponential of both sides. The exponential will eliminate your ln. Are you following right? We'll kick it off. So this is what we've got. X raised to the power 2 all over 4x raised to the power 2 minus 3y raised to the power 2 equal to cx raised to the power 2. Now, do you agree with me that you can divide both sides of this equation by x raised to the power 2? Because of course, on the left hand side I have x raised to the power 2. On the right hand side I have x raised to the power 6. X raised to the power 2 is common to both sides as numerator, so you can divide through by x raised to the power 2. If I do that, this will give me 1 all over 4x to the power of 2 minus 3y to the power of 2 equal to, this will give us cx raised to the power 4. Because you're dividing that x raised to the power 6 by x raised to the power 2 there. Good. There is nothing like a fraction in these options provided for us here. No fraction. So what is the implication? I've got to clear up this fraction by cross multiplying. Alright, it implies that 1 all over c is equal to x raised to the power 4, open bracket, 4x squared, and then minus 3y squared. Good. 1 divided by the constant of integration, c, will still give you a constant. You see, it's just like having 2 divided by 5. The answer you're still going to get to be a constant. 1 is a number, a constant. That c is also a number, constant of integration. Constant divided by constant will give you a constant. So that 1 over c, I can still choose to call it c. I commit no crime. That is something about the properties of constant of integration. And that will now be equal to, let us open up this part please and see if we're going to get any option there. X raised to the power 4 multiplied by 4x raised to the power 2 will give us 4x raised to the power 6. And then minus x raised to the power 4 times 3y squared will give us 3x raised to the power 4 times y squared. So I've gotten this simplified term, and if you look at the option, you would see clearly that we've got a particular option there, which is option D. So option D is the correct answer. C equal to 4x raised to the power 6 minus 3x raised to the power 4 y squared. Or you can decide to say 4x raised to the power 6 minus 3x raised to the power 4 y squared equal to C. It's still the same thing. So I've used this particular question to explain the application, how to make use of the Hallmarker's FDU, FNU homogeneous Fourier theorem. And I want to believe that how we will be able to quickly reduce this homogeneous equation to a separable variable equation is quite clear and fast using the Hallmarker's FDU, FNU homogeneous Fourier theorem. Let us move on to our second question. The second question reads, in which of the following equations is degree equal to order of equation? Now I've got the options here on the board. I'm just going to go straight to explain this. The concept of degree and order. Order is the highest derivative in the equation. Degree is simply the power of that highest derivative in the equation, when all fractional indices and all radicals have been cleared from the equation. Looking at option A, this is a differential equation of order 4 because the highest derivative of the dependent variable y in that option A is 4 times. Now, the power of this highest order is 1, which means that the degree is 1. Equation A is simply an equation of order 4, degree 1. Clearly, the degree and the order are not the same. Option B. Well, looking at option B, the order of the equation is order 3. You can say that, are you following right? The highest derivative of the dependent variable y here is 3 times. We cannot tell the degree here straight ahead except we clear this fractional index. And this fraction is 2 over 3, covering this whole term, 1 plus dy dx raised to the power 3. Now, to clear this fraction, you know that you have to multiply this fraction by 3 alright, so as to clear this denominator, because the LCM per se of this fraction is 3. So we're going to use the 3 to multiply this numerator. If you do that, if you cancel this 3 here, so you'll be left with power 2. Whatever you do to this side of the equation, you've got to do it on the right side of the equation. If I multiply this side, the power by 3, because this is raised to power 1 already, if you do 1 times 3, you get power 3 here. Which simply tells us that the order and the degree are what? The same. Is that clear? I can choose to write it out. Said we've got, because from what I'm saying here, option B is the correct one. If you go to option C is order 3, degree 4. They are not the same. This, if we are to move on to talk about the order and degree, we could say that this is order 1, degree 2. But although the dy dx is even scattered in this option, making it difficult to even talk about the concept of the degree in this case. Alright, so the correct option is B. Is that okay? Right. So all I've got to do is simply multiply this by 3, then come over to this 1 times 3. And then I'll now focus on this part, because the power of the highest order gives us the degree of the equation. So looking at this, this becomes 4, and then dy dx cubed raised to power 3. And so the correct option is option B. You can see that this is order 3 and degree 3. Option B is an equation of order 3, degree 3. The correct option is B. We shall look at our next question, number 3. The third question reads, solve by separating the variables dy dx equal to exponential x minus y minus x exponential minus y. This problem is a separable variable equation form of ordinary differential equation. And so we are required to solve by separating the variable. Of course, that is the procedure we use to handle a separable variable equation. So I'm going to do that. Let's see. We're given dy dx to be equal to exponential x minus y, and then negative x squared exponential minus y. I can rewrite this part, or this right-hand side of the equation, as exponential x times exponential negative y, and then minus x squared exponential minus y. You see, I've used the law of indices to deal with this part, okay? Multiplication law of indices. So dy dx is simply equal to this term. And if you look at this, you notice that exponential negative y is common to the two terms here. So we can do factorization. But watch out. Dy dx is equal to this term. Exponential negative y is common to these two terms. So while cross multiplying, so that the x will come to this side, I would like to factorize my exponential negative y. Is that okay? And so that is going to give us dy equal to, so we've got exponential negative y, which is common to the term. Then in bracket we have exponential x negative x squared. Then I'm bringing the x to that side. I've cross multiplied, and at the same time factorize the common term exponential negative y. This exponential negative y, at this point I'm going to separate it. Now you can notice that this the x term is carrying a y variable here. We don't need this y variable here, since the x cannot be a controlling parent of y variable. There's the x terms, they can go with the x, but this y will have to come with the differential coefficient, the y. And of course, bringing this term here is going to come as 1 over exponential minus y, which of course is inverse of exponential negative y. Mathematically, that is still the same as exponential y dy. That is if this should go as a numerator. Exponential y dy equal to exponential x minus x squared and then dx. So we've separated the variable. The dy coefficient is carrying a y variable, and then the x coefficient is carrying of course, x variables. So we can now integrate at this point. Exponential y dy, if you integrate that, you're going to get exponential y. That's equal to integral of exponential x dx is going to give us exponential x. Then minus integral x squared dx will give us x raised to power 3 all over 3. I am done integrating, therefore I shall add the constant of integration there, which is c. Well, I'll finish solving. Let's look at this answer I got and then the options provided here. And then you would see clearly that the correct option to this question here is option D. Exponential y equal to exponential x minus x raised to the power 3 divided by 3 plus c is the correct option. We shall now move on to our last question in this episode U21. Question number 4. The last question in this episode reads, what is the degree of the following equations? The 2y d squared x raised to the power 5 over 2 plus the 3y d cubed x raised to the power of 4 over 3. So our interest in this question is simply to determine the degree of the given differential equation. Is that okay? Looking at the question given to us, this is the differential equation, the 2y d squared x, and then the power is 5 over 2, added to the 3y d cubed x, and then the power is 4 over 3 equal to 0. So going straight, are you following? The first thing we have to do is to identify the order of this differential equation. The order of this differential equation is order 3. Y has been differentiated 3 times more. Are you following, right? So this is the order. Now the power of this order is what we refer to as the degree. Here the power is a fraction. You even have a fraction as power here. The rule, you must clear any fractional power you see or any radical before you can talk about the degree of that equation. Now this is 5 over 2 and this is 4 over what? 3. The LCM is what? 6. So we're going to use 6 to clear this fraction. But my focus will be on this because to get the degree, I must have to know the order first. It is the power of that order that gives me the degree. And so I will have no business here anymore. Are you following, right? I'll focus on this, the 3y, the cube x, clear the fraction there. Already we know the LCM is 6 as I already explained. So this is going to be the 3y and then the cube x raised to the power of 4 over 3. I shall multiply this by 6, which of course is the LCM, 6 over 1. Doing that, you would see clearly that 3 can divide 3, we're going to get 1, and then 3 can divide 6, we get 2. Multiply that 4 and 2, and you see that the result would give us the 3y, the cube x, and then raised to the power of what? 8. Therefore, the degree is 8. The degree of this order 3 term is 8, and that is the degree of this differential equation. The correct answer is option B. And this is how we've come to the end of episode U21 of our past question review on ordinary differential equation. In our next episode U22 on ODE, we shall look at the next question counting from question number 5. Remember to share our videos, like and comment on it, invite your friends to also join us as we prepare you in this course and also prepare you to smash your A's in ODE examination. See you in our next episode.